All right, this lecture will be on chapter 7 for physics. This will be momentum and collisions. All right. So we have a track here that I'll be using to demonstrate. I've got two carts. The one on the left is labeled A. The one on the right is labeled B. Initially, they're both equal masses, but we'll try that. And we'll use this for looking at momentum and collisions. So first thing, talking about will be on concept of momentum. And we use momentum is basically the mass and the velocity of the object. So like a train can be going very slow, but has a lot of mass, so it can have a larger momentum. On the other hand, a very small bullet can have a little mass and a lot of speed or velocity. So the concept, we use the capital letter P, or well, we use P, actually no a lot, but that stands for momentum, which is mass times velocity, and we put the little line on top to indicate that it's a vector. So it's the mass times the velocity, and it's in units of kilograms, meters per second, because that's kilograms, and that's meters per second. So that's the concept of momentum as what we'll be using here. So if I have an object, well, if I have these, take this cart, all right, moves at a particular velocity, the mass, the cart times the velocity is the momentum. Now it depends on the direction. So in this case, if we have, this is positive and that's negative, then in this case, this would have a positive momentum. In the other direction, have a negative momentum. All right, so it would depend on the direction it's going as to its sign as far as that's concerned. So it's very similar to what we've done in chapter 2 and other chapters related to this. So what we're going to get into now is the next part, our collisions. All right, so that's the main part of this chapter, is dealing with collisions. And in this case, we're going to be dealing with two different types of, to make it simpler, we're going to have what we call elastic collisions and inelastic collisions. And to make it simpler, we're going to talk about example here of elastic collision. I have these two carts. On one side, there's Velcro, so they can stick. On the other side, we have two magnets that repel each other, so that so they can actually sort of bounce off each other without actually touching. So what we have here, then, we're going to go to the extreme, elastic collision, totally inelastic collision. In this one, so in this case, let's look at this, right? So if I take B and aim it towards A, notice that what happens, we have a totally elastic collision, right? Because they're equal mass, all the energy is transferred from one to the other. There's no loss in energy between the two. So this we call totally elastic, meaning no energy lost. All right. So in the because we'll get into this idea of conservation of momentum and conservation of energy in collisions. And the other case we'll be dealing with is totally elastic. And what we have here is, in this case, if we use a Velcro on both sides, what we have is we hit one and then they stick together afterwards. So stick together after collision. Now obviously there are other cases, so these are extremes. We have totally elastic collision and completely inelastic. Now we can do something in between, all right, where it does something like that, and this one keeps going. All right, in this case, we have somewhere in between the two, but that's beyond the scope of this class. All right, this would be more for an advanced calculus-based class and so on. So we're again dealing with totally elastic, where All right, so those are the two basics we're gonna have. That's totally elastic and the other is totally inelastic. All right, so we're gonna have both these. So we'll deal with one at a time, and what I'm actually gonna do with this one first, because that makes it easier to deal with problems. So an example would be, all right, put these together, and I have one is going relatively fast. All right, and they're going to stick together afterwards. So I shoot it at it, and notice how they go slower afterwards. So I keep this stiff. Notice how the pairs stick together and go slower afterwards. We have conservation of momentum in any collision. Right, meaning P before, again, P is given by mass times velocity equals P after. And this is true regardless of the type of collision you have. All right, so for the most part, we're going to be dealing with this chapter in a conceptual basis, except for problems related to totally inelastic. So what would this be? All right. You know, example is in the book of the train. If you have a train and another stationary train, they couple together and move off afterwards. All right, what's the momentum before and afterwards? So let's take this example here. Both A and B are equal in size, so let's say both of them, MA equals MB is 1 kilogram, just to make it simple, and we'll say MB is going at, let's do it the other way around. Let's have it come this way. So we're going to have A come at B. All right. So V of A, we'll say is 2 meters per second, just to make it simple. V of B before is 0. All right. So conservation before and after. And the way this works is the sum of the momentum before equals the total momentum afterwards. So since this is a system, this would be MA VA plus MB VB equals, this is before, and then afterwards, it'll be MA VA after plus MB VB after. So what, let me put after is A. All right, and since, so this will be, so the momentum before equals the momentum after the collision. So it's going to be the same, and this is going to be true whether it's elastic or inelastic collision. The momentum is always going to remain constant. Now in this case of a totally inelastic collision, so totally inelastic, then they stick together afterwards. So that means that afterwards, VA and VB are the same. So this would be MA VA plus MB VB equals MA plus MB times V final. So that'd be the final velocity. So if we know everything, we can solve for how fast it's going afterwards. All right? So let's do an example related to that. Okay. All right. So in this case, I'm going to go back up here so I can keep my paper together. All right. So I'll keep my expression there. So in this case, I'm going to have, again, MA equals MB equals 1 kilogram, and VA is 2 meters per second, all right? And we're trying to find this. So this will be, oh, and VB initially is 0. So this will be 2, or 1 kilogram times 2 meters per second plus 1 times 0 equals 1 plus 1 times V final. All right, so that's 2. 2 plus 0 equals 2 times V final. So in that case, since momentum before equals momentum afterwards, this then implies that V, divide both sides by 2, V final is 1 meter per second. So it's half the speed, half the velocity of the first one was. So that's a momentum before and after in that case. All right. Now, if we look at that part, now there's another part here, is what happens to the energy, right? So that's momentum before. So we have this expression for an elastic collision, inelastic, and this is true regardless of whether it's elastic or inelastic. All right, so let's look at the next part of this. I'll leave that up, and I want to continue on because the next thing I want to do is deal with the energy of this system before and afterwards. Now for momentum, it's always conserved, before and after, regardless of what type it is. This is going to be the same. Energy, on the other hand, will be different. And so let's go on to that. All right, energy. All right, we're dealing with kinetic energy, and kinetic energy is 1/2 mv squared. So if we look at the kinetic energy before and kinetic energy after, all right? So for each one, it's going to be 1/2 ma va squared plus 1/2 mb vb squared equals afterwards 1/2 ma va final all squared plus 1/2 mb vb final squared. All right. So, all right, again, momentum before and after were the same. So if we look at this, again, mass is 1 kilogram, initial velocity is 2 meters per second. So this will be 1/2 times 1 times 2 squared plus, since that's 0, this would be just 0. And then afterwards, right, they stick together. So this will be 1/2 times, since they both have the same velocity, plus 1 times v final squared, which in this case, v final was 1 meter per second. So that would be 1/2 times 2 times 1 squared, which is 1, this is 1 joule. If we look at before though, this will be 1/2 times 1 times 4. This will be 1/2 times 4. This is equal to 2 joules, right? So what this means is we've lost 50% energy lost due to this inelastic collision. All right? So we have lost energy. Now, if this is an elastic collision, you can calculate cell, but in an elastic collision, and I'm not going to go through the whole calculation, but what we see here is, in this case, VA comes at a certain speed, VB leaves at the same velocity, so all the energy here is transferred to this one. There's no loss of energy. So in an elastic collision, no energy is lost. So in elastic, all right? So if we have an elastic collision, so this is the inelastic, elastic collision. Then we would have 1/2 ma va squared plus 0 equals 1/2. Well, that would be 0 because it's not moving afterwards. The first one is stopped. Plus 1/2 mb vb squared. And that would be 1/2 times 1 times 2 squared equals 1/2 times 1 times 2 squared, or 2 joules equals 2 joules. So that would be an elastic collision. So that's the difference. Momentum is the same in both cases, but in elastic collision, there's no energy lost. And that's true, so that's kind of what you'd like to have perfectly in an ideal situation is that. Okay, let me do one more here. Because in the text, we're only going to be dealing with collisions in one dimensions. The book gets into two-dimensional collisions. We're not going to deal with that. We're not going to, it's far more complicated than this. So in two-dimensional, you'd have one coming in, one scatters off to the left, one scatters off to the right, like maybe a pool shot. That is beyond the scope. We're only dealing with one dimension, And again, we're only dealing with elastic or totally inelastic. So let's do another example here, and then we'll go back to our totally elastic collisions. Inelastic. So what we'll do is we'll make this a lot heavier. What we're going to do is have one going at relatively high speed and hit together, hit like we do that. Now notice it doesn't slow down all that much as it collides into it. All right. So because this has so much momentum, we can look at this example. So in this case, just to make it kind of extreme, I'm going to make one a little more extreme than this. But let's say I have two, okay, and I'm going to keep my energy expressions the same, because I'll be dealing with that next. Right? Keep in mind. All right, so we're going to deal with strictly elastic collisions, inelastic, I should say, where MA is larger, in some cases much larger than MB. So in this case, say MA is 10 kilograms, MB is 1 kilogram. And again, VA is 2 meters per second, and VB is 0, right? All right, so what's happening here? So again, we have our expression for momentum, MA VA plus MB VB equals both of them together times V final. All right, so this would be 10 times 2 plus 0 is 10 kilograms times 2 meters per second equals 10 plus 1 times V final equals 11 V final. So in this case, that would be 20. This would be 20. Divide both sides by 11. And in that case, V final is roughly, let's see, about 1.8. Let's see, let's do 11, maybe 9, yeah, 1.8 meters per second, right? So it doesn't really slow down that much. Remember in the first case where they were equal, the velocity afterwards is 1/2. In this case, it does not slow down that much. So let's look at the solutions here. So again, we got 1/2, put in numbers. This will be 10 times 2 squared plus 0 equals 1/2 times, again, they're both together, 10 plus 1 times V 1.8 squared. Yeah. So this turns out to be 5 times, that's 20 joules. And this is 11, let's see, 3.6, 3.5 times 5.5. Oh, yeah, this is roughly 18 joules. So only about 10%. Again, I'm just doing rough estimate. So this is about 2 joules are lost. So this is roughly 10% energy lost. Right? So in the case of where A is much bigger than B, then less energy is lost. You can take this to extreme. You know, you're driving along the road at 80 miles per hour, and you hit a fly. A fly hits your car, it sticks. Right? You're not going to notice any difference in speed in your car. Right? Because almost no energy is lost because you have a much heavier mass hitting an extremely light mass. So we could take the more, we'd have less and less energy lost. So about 2 joules are lost approximately, so that's about 10%. So that's the case there where MA is much bigger than MB. Now let's take it the other way around. All right, what happens if we have it where B is heavy and A is light? And it comes in, all right, we can see in that case, it slows down drastically. So in this case, MB is much heavier than A. So this would be, say, this is 1 kilogram. And B is 10 kilograms. All right? Same thing, A is going at 2 meters per second, B is going at 0. All right, so what do we have here? This will then be, MA is 1, so that would be, let's get rid of that. So that'll be 1 times 2. I seem to have lost my, there we are. One times 2, so that'd be 2 kilograms meters per second equals 11 VF. So VF then would be 2 over 11, or roughly 0.45 kilogram meters per second. So this would be roughly 0.45 meters per second, or 2/11. So it's slowed down drastically. It's about 1. All right, now, make sure I have it right. It's 2. Yeah. Yep. All right, now let's do this case. We'll go back to here. In the first case where A was heavy, B was light, we don't lose much energy. What happens if it's the other way around? A light object hitting a heavy object. In this case, this would be 1/2 times 1 times 1 squared plus 0 is, again, 1/2, they're both together, 1/2 times 10 plus 1 times 2/11 squared. That's equal to 1/2 joule. And this is equal to, let's say 5, that's 4 over 121, that's about 3, yeah, that's 3 over 100. 3 over 100 is 5. Yeah. In this case, it'd be 0.14 joules. So in this case, we've lost more than almost 2/3 of the energy, more than 2/3 the energy. Approximately 70% is lost. So in the case of MA being much less than MB, then we lose a lot more of the energy. Now we can take this another extreme, all right? If we have, well, in some case, a tragedy is a light car hitting into a stationary train on a track or a semi, say on a stationary, the car will collide into it and then be almost stopped. There'll be the movement of the collision afterwards will be very little. So you're going to have, the greater this difference, the much more energy loss. I mean, it's the example of a fly hitting a car, fly coming in, hits it, basically everything stops. So all the energy is lost, either into sounds made or squishing of the bug or whatever. So, and that's the case there where we have a collision where a light object hits a heavy object, they stick together, much more the energy is lost. So that's the parts of collisions we're going to deal with. Totally elastic, totally inelastic. All right, the last thing I'm going to do with here, and this will be for chapter 7. Basically, this will end up being all of chapter 7 for today. We'll save the rest of chapter 7 on center of mass for the next test, as far as that's concerned. So that'll be section 7A. We'll deal with that center of mass in the next section. Next exam, for exam 4. Okay. So what we're going to have here, I'm going to do one last part because we have a quiz called the Ballistic Pendulum under chapter 7. And the Ballistic Pendulum quiz is very straightforward. And so under chapter 7, all right, we'll be having I'm going to move into another pen. Worn out. All right, a ballistic pendulum. And this is also a quiz, which includes a YouTube video in the quiz. And it'll show, what it'll show is a pendulum, right, with lines across to indicate height. And this is a relatively large mass. And what's going to happen in this case, and this is a ballistic pendulum, this is actually how you can measure how fast a bullet is going. I mean, this is how you can do it without a high-speed camera. So you have a light bullet, which has some mass, moving at some speed v, naught. It then hits the mat, hits this together, and because it has momentum, they stick together as an inelastic collision, and will cause the whole thing to rise up a height. All right? So what you're going to have is this will hit it, they'll stick together, and the whole thing will swing up for some height y. So what we're going to have is a couple things here. We'll have, based on our equations of potential energy, all right, so this will be little m plus that, so the bullet's there. This will rise to a certain height. The potential energy that it has gained from the collision is m plus little m times g, and g is 9.8 meters per second. Again, g will be 9.8 meters per second squared for this particular example because we're doing a very precise experiment, times the height y. So based on that, we can get the potential anyway. We'll have the mass of both, we'll have g, we can measure how high it goes up. From that, we can go back to the original kinetic energy. You'll see this, be 1/2 m plus little m v squared. And this will be after the collision. So after this collides, I mean, this will be coming at a very high speed, they collide and go up a certain height. V final. In this case, these two are equal, so you'll calculate that. You can calculate that, given the mass of both. And in the lab, you get, in the quiz, I should say, you get both of these together. From that, you can then solve for the momentum before. Right, so before the collision, it'll be P before equals P after, and that'll be, after will be M plus little m times V final equals M little m times V naught plus 0, because it's not moving at all. All right, so from that, you can then calculate what the initial velocity was. So this will be a very light bullet. This is a real problem done at a real video, and you get very good answers for this lab. So this is all of chapter 7 is concerned. And you can get into this section. So this is again part of the last section of 7.6. Last part is again ballistic pendulum, and deal with some problems related to that. So that's chapter 7. Next part I'll do is chapter 8 for the last part for exam 3. So have a good day, and I'll leave that up.